So what does it mean to integrate a function f that's a function of a single variable? In other words, what does it mean to compute the integral from a to b of f of x dx? So let's draw a picture of the graph of f, and it looks like this. And let's draw the interval from a to b. And what it means to compute this integral is that we're going to take this interval that we're integrating over, and we're going to chop up the interval into tiny pieces like that. And then we're going to compute the contribution of each piece, and then we're going to add up all the individual contributions, and that's going to give us the value of our integral, at least to a good approximation. Now, what do I mean by, how do I compute the contribution of each piece? So let's, this point A, let's call this x naught. And then this number here, let's call this x1. And this number here, let's call this x2, and then x3, x4, and then finally b is going to be called x5. And in the general case, we would call this x sub n, because more generally, we don't chop up our interval into just 5 pieces, we chop it up into n pieces. So now, the next thing that we do is, for each of these subintervals, we're going to pick a point arbitrarily that belongs to each of these subintervals. So this point here that I just selected arbitrarily, I'm going to call this x naught star. And then I'll pick a point here, which I'm going to call x1 star. And then I'll pick a point in this interval, which I'll call x2 star, and so on. And how do we compute the contribution now of this first subinterval here? Well, what we do is we draw this rectangle. We draw this rectangle that looks like that, and we compute the area of this rectangle. And the area of this rectangle is just base times height. The height of the rectangle is f of x0 star, x naught star, and the base is delta x. We'll call it delta x, the width of this subinterval. This here, this area of this rectangle, is the contribution of the first subinterval. Now let's compute the contribution of the second subinterval. So now I'm going to draw this rectangle. I'll draw this rectangle here that looks like this, and I'll compute the area of this rectangle. And the area of this rectangle is, again, base times height. The height is now f of x1 star, and the base is delta x. So here we have the contribution of the second subinterval. And then we do the same thing for the third subinterval and the fourth subinterval, and then finally the fifth subinterval. So I'll put dot, 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 and then the contribution of the final subinterval is going to be f of x n star times delta x. Here, remember, here's our final subinterval. So we are selecting a point arbitrarily in this final subinterval. Oh, this should be x n minus 1 star. So this point that we just selected that belongs to the final subinterval, we're going to call this x n minus 1 star. And then let's draw this rectangle. And let's compute the area of this final rectangle. That's what we've done here. That's the contribution of the final piece. And then when we add up all these individual contributions, what we get is the area under the curve from A to B, the total area under the curve from A to B, at least to a good approximation. So the integral from A to B of f of x dx is approximately given by this sum. And this sum is called a Riemann sum. Now you might say, this is only an approximation. How do we get the true area under the curve from A to B? Well, you could imagine repeating this process, but using smaller subintervals. And if you use smaller subintervals, so delta x is smaller, then you're going to get a more accurate approximation. And then if you want an even more accurate approximation, you could do it again, now with delta x even smaller. So the true area under the curve from A to B, the true value of this integral, is a limit of Riemann sums like this, where it's a limit where delta x is approaching 0. So this integral is actually a limit of Riemann sums like this. But the basic idea behind integration is you take the region that you're integrating over, you chop up that region into tiny pieces, you compute the contribution of each piece, and you add up all the individual contributions. That's the idea behind integration.